26 people have joined. Shall we start?
Oh, yes, whenever you like.
Yeah. Okay.
Yeah, go ahead, Aruna.
Yeah. Okay. Welcome, everybody. Today, we are happy to have with us Professor Kameswara to deliver the 8th IIA-50 commemorative lecture. Professor Kameswara does not need any introduction at IIA. He is a well-known astrophysicist, a leading stellar astronomer specialized in studies of hydrogen-deficient stars and related objects. He did his MSc in 1965 from Osmania University, Hyderabad, and obtained his PhD degree from the University of California, Santa Cruz in 1974. His PhD thesis, entitled A Study of the Colors and Spectrum of Our Corona Borealis During Minimum Light, was conducted under the supervision of Professor George Harbeck. In 1975, he joined IIA and served the institute for long 32 years until his superannuation in 2007. As a member of the institute, he had served as the scientist in charge of the Vanuatu Observatory for a number of years and as the chairperson of the group committee Stellar and Galactic Astronomy from 1990 to 1996. He was also the Dean, Faculty of Sciences during 1996 to 2007. He is still very closely and actively associated with IIA. His main research interest includes hydrogen-deficient stars, RCBs, observational studies of stellar evolution, circumstellar dust, and UV astronomy. He led the team that had constructed the fiber-linked Coude-Echelle spectrograph attached to 2.3-meter Vanuatu telescope at the Vanuatu Observatory, Kavalur. Along with a few enthusiastic colleagues, he made an early proposal for an Indian ultraviolet imaging telescope in space. He was actively involved with the Ultraviolet Imaging Telescope, UVIT, one of the payloads on board India's first multi-wavelength astronomy observatory, ASTROSAT, launched by ISRO on September 28, 2015. Professor Rao has been deeply interested in Indian art and architecture. In order to trace the development of observational astronomy in India, he had conducted several archaeoastronomical studies and also studied diverse architectural monuments. He is actively associated with many professional organizations. He is a life member of the Astronomical Society of India and an active member of the International Astronomical Union. He received the 1989 Sri Hari Om Ashram Parade Dr. Bikram Sarabhai Research Award in Space Sciences. With great pleasure, on behalf of the IIA-50 Organizing Committee, I welcome Professor Kameswara to deliver his lecture, Ultraviolet Astronomy in India and IIA. Over to Professor Kameswara.
Thank you, Aruna. It was very kind of you, such an elaborate introduction. And so I was rather embarrassed. Okay, after receiving this kind invitation from Aruna to give a selected topic and then reminisce for the occasion of IIA-50, and I looked up my laptop dictionary, and the reminiscence says the grandparents sat there reminiscing all afternoon. I am a grandfather. So in the guidelines given by the dictionary, I thought I'll tell you a grandfather's tale on UV astronomy, how it started at IIA. And let me start with my initial introduction to IIA. My marriage and joining IIA happened almost at the same time, slightly, maybe less than a month apart, exactly 45 years to the date. We have been together ever since. Entirely my pleasure. Oh, entirely my pleasure. I had I would have joined IIA a little earlier even, but a few misconceptions I had when I started coming back to India in 1974-75 period. One of the misconceptions was that once you're a Hyderabadi, you're a Hyderabadi for life. And so all Hyderabadis would like to get back to Hyderabad. That was one of my. And what a Hyderabadi is takes another afternoon to describe. But now, regarding the second misconception was that when I was thinking of coming back to India, then I was looking for jobs. My friend Daya Gilra, who was earlier in India, he was also looking for a job. He met Bappu in Bangalore and told him that I am also interested in coming back. And Bappu told him, I believe that you ask him to write to me. But instead, I wrote to Professor K.D. Abhankar, my guru in Usmania University, saying that I would like to come back and would need a job. I got an immediate reply from him saying that, oh yes, welcome, come back here. We have some positions vacant in Usmania University Astronomy Department. As soon as you get here, I will try to get you a job. And my misconception was his ability, his ability in influencing Usmania University authorities to heed to his wishes. Once I got back, I had to run pillar to post without much success. Finally, he told me, you get a job somewhere else and come and threaten these people that you're not going to stay here unless they provide you with a job. I said, this is kind of ultimate, and I applied to IIA. Thus, my association with IIA was disdained. To give you a flavor of how IIA was in those days, is shown here in this slide when people were most fearful. And I can point out to you the people, some of them you might be able to recognize. The man with the suit on the left is Professor MKV Bappu. And next to him on the right side is Ashok Pati, who in his lean days with a beard. And another man with the suit was Jayarajan, who was our optics expert. And next to him is yours sincerely. And next to him on the left is Dr. Ghansham Shah. And in front of him was Professor Bhattacharya. And I don't know whether you can also see a few others whom. So another closer look of the same scene where everybody was laughing, and that's how it was in IIA. Many a speaker in this series talk about how liberal IIA was towards research topics and towards research attitudes. I took a full advantage of such a situation and tried to do astronomy through various means, from rocks to radio telescopes. I mean, rocks, I mean, old megaliths, big rocks, and not quite dug up burials, but surveyed ancient, old graves, dolmens, which are called, and some prehistoric paintings, temples, and then from satellites to where through collaborations we could try various satellites from UV to infrared, and then also dabbled in radio astronomy to ELA, CEST, and even GMRT. My friend David Lambert used to often quote Auden, W.H. Auden, in his usual quote was what it is. It takes little talent to see clearly what lies under one's nose, a good deal of it to know in which direction to point that organ. My nose went all around 180 or even more degrees. So one of those adventures was embracing UV astronomy or jumping into it. Now, of course, IIA is the seat of UV astronomy in the country, with several people, the high priest of UV astronomy, Giant Murthy, who won't touch anything unless U is written on it. And people like Annapurni, Subramanyam, uh, Stalin, Firoza Staria, and their associates. So now it has become a center for nuclear, several UV pundits. But in IIA, once initially it was started very casually, and it happened in Kavalu. That was in 1979. Professor Bappu was elected as the IIU president, the General Assembly, in the General Assembly in Montreal. Invitation to visit NASA at Goddard, and somebody showed him this facility uh, of operations with IUE, International Ultraviolet Explorer, which was launched in January 1978. He was quite impressed, and he came back. That winter, I was observing in Kavalur with 1 meter telescope, and he he was also visited that one night, and he used to usually stay there in his first floor of 1 meter telescope. On the left side was his bedroom, and the right side was his office. And those days, the allocation of accommodation was purely by hierarchy. Director used to the first floor, leaders and above used to occupy the ground floor, and pedestrians and fellows like us used to be in barracks called Lab A and Lab B. So one night after finishing my observing in the morning, I was walking back towards my lab accommodation, and I heard this shout from through the window. He called me. So I went back. Then he explained that he received an application for time with a UE satellite from his friend in Edinburgh, Kashi Nandi, and we don't have much time. We had to fill it up that make a proposal or two that day and send it back so that they can receive in 4 or 5 days in Edinburgh. Then they had to get his director of Edinburgh Observatory signature, then submit to SERC for time allocation. So the whole day we worked, and we came up with two proposals with IESAT for IESAT. One is that by his interest, Dr. Bapu's interest, it was looking for chromospheric emissions in Cepheid pulsators. And the other one was I came up with my interest in our corona borealis, which Aruna already introduced you, hydrogen deficient carbon star. That whether it has any chromosphere, and then can we see the chromospheric emission and magnesium 2 lines. So we managed to finish that application proposals, and the next morning he took it to Bangalore and sent them to Kashi, and finally Kashi could get one of our proposals got successful, and we got time to do our corona borealis. See, in any Indian, there are two characters in who can get into any narrative on Indian astronomy. One is MKB Bappu, the other is Meknath Saha. And Bappu told me, I also introduced me to Meknath Saha's interest in UV astronomy. It's astronomy about, what he used to call stratospheric observatory, that going above the atmosphere. He gave a lecture in 1936 at Harvard emphasizing the importance of going above the atmosphere to study ultraviolet spectra. And that you can find in Harvard Observatory Bulletin 905 in 1937, which is, I will just read it to you from the slide. But access even to these limited regions will result in invaluable addition to our knowledge, for they will offer information about the behavior of the resonance lines of most of the elements which occur in the front half of spectrum. He was talking about H, lemon alpha 1260 resonance line at 1640, and lithium, continuum, and magnesium, two lines at 2800, so on. He was the second astrophysicist to say, after Albert in 1923, the relative importance of going to ultraviolet and to the outside the Earth's atmosphere. So the important, the interesting and most uh, important things once you go outside, apart from the lack of atmosphere, in which you can get diffraction limited images, you could also get the accessibility of the whole electromagnetic spectrum almost. And when the why you had to go to a space is shown in the first view graph on the left side, where the if you had to look from the top down, that is the radiation which is incidents get diminished by 1 by E factor at these heights of our Earth's atmosphere. For example, you see, you can only see the region between 1200 to say 1800 only if you go above 120 kilometers above. And whereas in mid ultraviolet, if you go above 40, you can still do it. So this, so that's the reason why one has to utilize space-based vehicles. Second thing is the relevance what Saha was pointing out. The many elements have their uh, resonance lines. For example, hydrogen, carbon, oxygen, and so on and so forth. Above 1500, about 1000 in different stages of ionization. So this you cannot get from the ground-based observations. Most importantly, and interestingly, is the sky background, which is very helpful in in the ultraviolet. As you can see, that ground-based optical background comes around 22, 22.5 for square second of arc, whereas in the ultraviolet, it is 4 or 5 magnitudes fainter. So even with a small telescope with longer integrations, you can achieve almost the same flux levels as with a big telescope. So these are the advantages which were realized by people. And 1946, the famous Rand Corporation report, which Lyman Spitzer wrote, was instrumental in really starting the space astrophysics explorations. He was also the one who predicted the galactic corona, and OAO3, that's Copernicus, was essentially devised as thrown to detect this galactic corona. So unfortunately, Saha's Saha's contribution about our emphasis on importance was mostly neglected by everybody else, except until Bapu told me this. So now coming back to that, our proposal and the UV, which is started, that was the first attempt of UV it's being done from IIA and also probably in the country. So where I had to make a trip to University College London, where I was trained how to use the UV satellite, and then from there I went to Madrid. And there's Pilspa. There we did the observing with the UV satellite, and the result of it was published in the monthly notice as a letter. And we could see this gamma sig is a normal supergiant. Orcor-Bohr is the peculiar supergiant in which we're looking for the magnesium 2 emission. In the core, we see the signs. The two resonance lines of magnesium are shown here. So that was the beginnings, and then not only it's the beginning, it's also a beginning of a good long last friendship with Kashi Nande, who was at Edinburgh. He was already worked in the UV Astronomy with TD1 satellite, and they produced a big catalog. And we also collaborated on several other things. We made a proposal to IRAS to do the first infrared survey observations for Orcor-Bohr stars. And so we got some time and did that was another paper. The activity in the country those days was centered here and as well as in TAFR, where Tarafdar, Krishnaswamy, and Vardya, they were looking at CO molecular absorptions around hot stars, interstellar medium, and BE stars. And I think Prahlad Agarwal was also looked at some of the active stars like RSCVN with IUE. Most of this activity was IUE through guest observer. This proposal says they're collaborating with other friends abroad. And as we see, the UV satellites, including IUE until 1978, are mostly either photometric or spectroscopic. So either VO1 ended up in Indian Ocean, VO2 to Copernicus to IUE, all of them are spectroscopic satellites. There was no imaging, though one can get diffraction limited imaging from the space. And it occurred to me, why don't we start doing imaging comparable with a kind of second of arc resolution, spatial resolution. When the two-dimensional detectors were available, for example, IUE used to use the two-dimensional detector to record the shell spectra. And you hear so many glorious things about Indian Space Organization launching their launching capability. And I thought, okay, why can't we try it in India? Is it possible? But then I I had no influence, not this thing. So except thinking of dreams, we can dream of doing that. Saying that it's like this R.K. Lakshman's cartoon where you are growing a flower on a rock. So that kind of what, difficulties were usually we never. So, but luckily, what happened was in 1988. Kasturangan and Krishnan Marar, they were in ISAC that time, asked for proposals for payloads on Indian satellites triggered by their X-ray experiments with earlier satellites. So we thought we were excited, and a bunch of us from IIA, I think there are Ashok Pati, probably Prabhu, and a few other youngsters, even Venkatekrishnan might have been there. We all made a proposal for a satellite-based UV telescope. I think it's 50 centimeters. And so there was a meeting in ISAC, and there were people like U.R. Rao, Srikantan, of course, Kasturirangan, Rad, and we presented. And there were about nine to 10 proposals, mostly from TIFR, and one from us, from IIA. And finally, they listed the priorities. Ours was surprisingly the second one. Well, it remained so as a proposal for some time. Meanwhile, UV8 ultraviolet imaging telescope was by Hopkins, I think, was launched as a space shuttle in 1990 and 95. the 10-day period, it was flown, and it's a 38-centimeter telescope in which they imaged the sky in a few important objects. But that was a kind of short period trials. So there no consistent imaging facility in UV was available. And it so happened in between 92, 93 or sometime later, Prahlad Agarwal, and if I remember correctly, even Judge Joseph visited IIA, and for some reason we started talking, and they said they came here with an idea. They wanted to put a X-ray payload on a satellite, but they wanted optical monitoring. So they came to inquire whether we'll be interested in putting up an optical monitor along with their X-ray payloads. Then I took a chance. I said, look, I mean, instead of optical, you can do even monitor from the ground. Let's do ultraviolet. And that's how the idea started. And then there was a meeting in ISAC and organized by Dr. Kasturirangan. By that time, he became the chairman of the Israel. And many astronomers from all astronomical institutions gathered together, and various proposals was mentioned, and the chairman appointed two working groups. And you can see the working group members. These working groups are assigned the job of coming up with appropriate possible payloads for the astronomy satellite, Indian astronomy satellite. And we met, discussed, and so on and so forth. There was a joint meeting in January 1997. We all consensus in saying that infrared is untenable because of its cryogenics are necessary. The whole telescopes have to be cooled, and detectors is another problem. So we came up with X-ray payloads, and as well as ASTROSAT includes an optical and ultraviolet imaging telescope covering 1,000 to 3,000 angstroms UV bands, complementing the X-ray observations. But it was decided to have collaboration with Kennedy. That time, detectors, UV detectors, is a big problem. I mean, we don't have the resource. How do we get it from this thing? We were trying to explore the possibilities of collaborating with us. I don't know how Canadians were also trying to fly another satellite similar to what we were thinking of. But they couldn't get it through because of lack of funding. Maybe we thought we can collaborate. I think Jayant Murthy was probably put us to Canadians. I think he had some contacts. I don't know whether Jayant joined by that time our institute. But in any case, that was the kind of final consensus. And then we are decided to make a proper proposal to the DST, putting all these our payloads and the details to be submitted as a formal proposal. And we started working on it. UV part was to be done by us. Ashok Pati even worked quite hard on this with us. And then we came up with a proposal containing a 50 centimeter telescope, which from 1200 to 3000 angstroms, with a dichroic for a single mirror, with a dichroic which will bifurcate near far UV and near UV, and several details are worked out, and so on, the plan of action, and so on and so forth. This is also published as a spy paper in 1998. Then we and Prahlad Agarwal worked out the other part of the proposal, all the three payloads, hard X-rays, soft X-rays, and Sita and others. I think they did the transients. So a combined proposal was submitted to ISRO to Kasturirangan in sometime in 2000. Dr. Agarwal came here to Bangalore with a letter from their director saying that they will support this proposal once it is accepted by ISRO. And then I took the letter from Professor Kausik, who was our director then, saying that that will be supported. And then Sri Kumar Agarwal and I, we three of us went and formally submitted this proposal to Chairman ISRO. And this is the front page of that, and various groups, who is going to do what. And our ultraviolet telescope was contained all kinds of names: Kaushik Joshi from PRL, Mahesh Jayantmurthy, Ashokpati Saxena Optics, and Rakhandra Prasad for our cryogenics, for laboratory establishment, and Sam Ragland, who was a postdoc that time here with us too, for the detectors, and Gangadhara for software and image restorations and all that. So with and Mahesh was also there for mechanical. And so this formal proposal was made to ISRO that then it started the real several at-cost meetings were taking place to discuss these proposals, and we were struggling to do. At the same time, you see, HCT was coming up until 2001 and so on. Our technical manpower was locked up. We don't have a separate manpower as exclusively for us to work on these things. All these gentlemen who mentioned, each one is took up one part. For example, Ashok Pati took interest in devising this mechanical structure and filter and so on and so forth. Giant, the software part of it, and the detectors, and we had filters. So all that, and section of the optics, all this thing is being done by their enthusiasm. And we didn't have an exclusive team as such formally done. So, and then we didn't have resources in the sense. I go and ask Kaushik, then he says that, okay, let ISRO accept it. We'll provide the money. Money is not the problem. I'll get it from DST, but get the former. And in ISRO, they wanted a well worked out, where is your teams to do this, you do that, and all kinds of things. So we were caught up in between these kinds of. And then another problem is to test. UV needs to test or to calibrate. All that was it had to be done in very clean rooms as it gets skilled in. So you need to develop very high 100 class clean rooms, and so you need separate labs and various to make various tests, and that is a separate establishment which might cost another 10 crores in a 10 crore project. So how would you present? Srikantan used to tell me that even if we spend that, it's only one time use. How do you maintain this? Even to just keep it running, it's very expensive. So we were caught up with all kinds of these things. In spite of that, we we did, and also I think I and Jayant visited Canadians in Ottawa and talked to the Canadians, especially through John Hutchings, to about the Canadian collaboration on the detectors, and we somehow made them to come collaborate with us, and all these things were developed. We had a kind of review meetings of whole proposal in various parts, and I think Tandon was the chairman of the committee who was to examine on behalf of ADCOS and so on before recommending it. So, but this was caught up, and neither day it was formalized. There's not much money. That time I was as a dean. I had little bit of leverage, so I used to meddle some money to get monochromator and few other things. You, so, but that is a kind of you know bonus. But real, we didn't have dedicated manpower as such. So things were a little slow on this thing. And secondly, whenever we, though in spite of all this work being put in, whenever there is, ISRO used to call for review meetings at convenience of probably the chairman or something. They won't tell you when exactly they're going to have this meeting. So, and even if you tell them that you will be away for some time and so on and so forth. So once or twice, I think Ashok and Jayant were caught up meeting. They suddenly called in Bombay, and then they started blaming, "Where is your PI?" And he's in some abroad enjoying something, so on and so forth. So there was all kinds of problems, but in spite of it, quite a bit of work was done, and then the proposal. By this time, from a single telescope to we thought two telescopes, one dedicated to the far UV and one dedicated to the near UV and optical would be the best to optimize the far UV transmit, which is going to be anyway slightly less sensitive than the near UV. So most of it, but one of the important things we kept on uh, harping about or insisted that we should have a telescope which has a 1 second of arc resolution or near to that. In between, there's a 2003 Galax was launched, and luckily they had a survey. One of our prime motivation to do that is also UV survey of the sky, and most of the survey part was taken up by Galax, but their spatial resolution was around 5 to 6 arc seconds. So we are about 5 to 6 times better. And we are, of course, HST is 10 times better than ours. But that 1 second of arc resolution is compatible with what we do in a good optical observing. So this complements ground-based observation. That was the main idea behind insisting on that. And that has become very useful. And very defining moment in this story is happened in 2002 February. I was in Texas or somewhere. Then they sent a email that we are arranging a meeting. You have to come and finalize this thing. And chairman was not very pleased at the progress of UV telescope UVIT, and then we had to take some drastic decisions whether to include this in this or not. Then I came back for this meeting, and the previous night, Srikantan and Kaushik took me to dinner and said about, that they were very unhappy. They might even change the change the management stuff, and they might even drop and so on and so forth. So I was prepared. I said, okay, as long as it's going up, the other things don't matter. And of course, everyone recognized the importance of UV. See, this will be a unique experiment, whereas the other payloads, X-rays, are also being done by others. So there is nothing really to compete with this telescope in the time near future, and so it will occupy its own importance. So that just seemed to have been realized by everybody. And this meeting has happened, and things have changed. Then two things happened. That there's a project board was formulated with the Yashpal as chairman, and Sham Tandon was brought as a project manager with with the independence of operations and so on and so forth. And he could. That was one good thing in a way because all the doors were open to him. Then and many others. So, for example, until that time, ISRO, whenever you go and talk with the optical people, can you do this for us? So, no, we are too busy, we can't do this. But whereas after these meetings, they took up of even making the optics themselves, and so many things became clearer. And for the MG came in lab, the allocation of money and so on and so forth. And then, so things became much easier, and they could recruit young engineers, several people, and things progressed much better. And the final configuration which was came up with was the similar two telescopes, base one dedicated to the for UV, one dedicated to the near UV, and these are the which are essentially the requirements essentially are the same as earlier, and materials and so on and so forth were dedicated teams have formed and championed and formed groups not only here in Ayuka, and he brought in Kosh to help in the electronics and so on. And, so and this is ASTROSAT satellite up there with the two imaging telescopes, UV and X-ray, and this is the final configuration almost. I seem to be running out of time. So this was the PDR which was submitted into 2006, which every aspect of this project was dealt in detail and was submitted. Even in 2003, we had to resubmit another version of the proposal, UVIT proposal, separately. Uh, my involvement was that time was mostly science and to some extent data, I suppose. And slowly, we even had very interesting, several meetings to discuss various scientific and technical aspects of this ASTROSAT, one in IIA 2006. You can recognize several of the stalwarts in here. Jayant Murthy, in the back is Anand Rao from PRL, and KP Singh and Soft X-ray man, and it's John Hutchings from a Canadian. Behind him is Patrick Court. Uh, and there's Stewart from Leicester, who was helping, working with KP on soft X-ray telescope, and Prahlad Agarwal, and various Ashok Pati, you can see in the back, Yar Rao, who was also doing the hard X-rays, and so many others. We used to have these meetings not only here, even abroad, and we all went to Montreal, a Canadian invitation, and then we had discussed such collaborations and progress. Until that time, there is Koteshwar Rao, who was the project manager for ASTROSAT for quite some time, and Manchanda is next to him, who, who was doing this hard X-rays. And so these things went on, and this I just showed you the final specifications. From now on, I'll come to the almost, just before the launch, everything was finalized. This is final configuration of UVIT, and these are bound by this what do you call ring, which joins these two telescopes. All the payloads on ASTROSAT are pointing in the same direction. So these two UV telescopes have to look at the same point of the sky. So they have been joined together, and these are the details about the mechanical structure. The back focus, the back plane, and various instruments which they could go into, spacers and so on. And meanwhile, this MG came in and lab where the clean rooms and test equipment has set up for these collimators and so on to test that two UV telescopes were developed, and mainly I think Raghvendra Prasad and Sri Ram and several other, and Theravan and so on. I don't know. I don't remember all the names, but many people were involved in that, and they all worked very hard to develop this, establish this clean rooms, and the UVIT was tested, and there in those clean rooms, and the various aspects of the collimation, the focus, and the thermal, and so on and so forth, variations. So these are various fuel gas which illustrate that various tests being done. These are the clean rooms in Professor N.G.K. Meenan's lab. This is a 10,000 class facility where most of the integration work of UVIT has been done. And these are two UVIT telescopes in those rooms there. UVIT telescope up there. And so it was they were ready much earlier than other instruments when the payloads flying time has come closer in 2015. And this is the total ASTROSAT, they're ready to be put it in the rocket. And I would like to emphasize that is our very first attempt at UV experimentation. We haven't done anything so far until this time, and even this at such a sophisticated level to really realize it was a major achievement. I think we shouldn't underestimate that. We are very proud of that kind of thing, and particularly all the people who were involved in that. And when I was very thrilled when I got an invitation for the launching occasion of the launching of the satellite. We all went to Sriharikote, and then that was a real thrill to see our satellite go up. And so now it's just completed. UVIT has completed 5 years in orbit. Congratulations! It should be really, though near UV telescopes are functioning 2017 or something. But then it was even now the far UV is very good to do many challenging things and has been doing that. And certainly we should congratulate everybody who is involved in that. And also the project manager Sham Tandon was really he worked his very hard to get the things up. And there are many exciting things science which has came out of that. And we recently had about the paper in Nature of the galaxy at Z of 1.42 or something, and then many more things. So I will try to illustrate you some of the science which is being done, and is a kind of personalized version of it, and some of it maybe would have involved and few others. So let me show you what. One of the major items which is observations of star cluster. Blue stragglers, the favorite activity of Annapurni Subramaniam, and we joined in few of them. And I think this is one of the first papers which was looked at the NGC 188, which is a galactic cluster of stars, which had this blue straggler, and which is marked there. And blue stragglers, the nature of the blue stragglers is under debate whether it's, of course, suspected to be consisting of two stars. And the nature of the second unseen star is what was to be explored. And this was it's called WOCS 58885, and the optical part was like a 6,000 degree temperature G star. And the UVIT observation showed that the energy distribution extends far into the ultraviolet. And when you looked at it, there was what sort of star it is. I mean, it's probably what I think is. I don't know what the. No, I forget exactly the T effective temperature, which may be 13 or 17,000 degrees. But the interesting thing is when you look at the luminosity of it from the ratio of these fluxes of that, the luminosity of it, it seemed to be not right on neither a subdwarf or a horizontal star, but is more luminous than that, and which led us to think that it is the post-HGB star in transition. So, and then previously, as opposed to GB stars, it probably underwent mass exchange with the companion and be active and become a blue straggler. The another one example is this blue straggler in the globular cluster NGC5466, so-called NH84. You can see the cluster diagram there. Many of the blue stragglers are concentrated to the nucleus, whereas this lone object is in the corner of there. And that has been analyzed again by Snehalata Sahu and company. And again, this UV8 is instrumental in discerning the hot star, and that turns out to be it's a 30,000 degree white dwarf. Uh, so these are many. They could survey many more, both in galactic clusters as well as in globular clusters, and it's a very interesting area of investigation to discern the nature of these stars, which are blue stragglers have been known for a very long time, but not really could be established what their identity and their distribution, whether they're captures and whether they evolved as together in common envelopes and so on and so forth. That's it. This is a cluster, global cluster. You could see the optical part on the left side and the UV part with UVIT on the right side. So see whereas the crowded photometry in the optical would really be to do, whereas in UV the hot stars only pop up and you could see them isolated with our resolution of close to 1 second apart. It's really very very interesting to discern the hot star population and their properties, like the horizontal branch stars, blue stragglers, and post-AG B star, extreme horizontal branch, and so on. Their number, densities, and proportions, lifetimes, various things could be studied. And one of the examples where it's studied is NGC 288. Another area where which I'm also involved with Firoza Sutaria is this Cygnus supernova remnant. As most of you know, the importance of supernova remnants comes because it's an eject of the big massive star and very chemically enriched the interiors. So these interaction of these ejecta with the interstellar medium as well as with its own winds is a very interesting area of investigation. How chemically mixed it is, how much it interacts with what are the shock velocities and various physical conditions. So these can be arrived at if we know the diagnostic lines and the distribution, especially and along the remnant. So various emission lines come through the various filters which we have in UV80. For example, carbon 4 comes through the filter which is centered around 1680 angstroms or so. So these various lines, these images of various lines which are probed to map this high excitation to low excitation ionization structure from which you derive physical conditions, ultimately maybe even to the abundances, which the anomalous, whether it is abundance are distributed uniformly across or not. And these are beautifully, textured images which came because of the high resolution of UV80. And there's some more details, which is coupling them with X-ray emission to UV emission to build up the whole physical model of the whole, all the physical conditions to be modeled ultimately. Now let me go to this is the our nearby galaxies have been probed or intensely being observed by our Canadian friends, John Hutchings and all the associates which are mentioned here. Luciana Bianchi and Lee and Post, all these collaborators. And John Hutchings sent me these images of the nearby galaxies like SM field. Again, what he's repeating the importance of UVIT compared to the galaxy and other things. See, this is a small field in SMC. That blob of this thing on the right side is 47 TAC, which is a globular cluster. And that same population in the far UV calcium fluoride window and then near UV in silica. So you could see that far UV number of stars are much more, well, not really so drastically, but the much bluer stars are prominent and not as much crowded as in. This is a combined image of that, and these yellows are near UV, prop up on there. Stellar populations is being studied by them with various diagnostics. For example, the colors between various uh, UV bands are shown sensitive to the temperature and the extinction. And so these are being used to study the population distribution. This is M31. I'm rushing because I'm almost close to my assigned time, but let me quickly show you these beautiful images of M31 is so big that you have to get 8 points to get the whole region. The central part is being shown here. The galaxy on the galaxy image, the circle describes the part which is captured by the central part of UV81 pointing. And you see the contrast between the nucleus in optical on the left side and the same nucleus in UV. And there's only you see hot stars in the UV. So that's the distribution of it in the arms and the nuclear bulge. And these are being intensely studied by our friends, Canadian friends. And they did population no, since studies. Not only the individual point sources have been identified and compared with HST images, and they came up with 75,000 sources in identified in UVIT images of that. And they also did the coincidence with Chandra and came up with the X-ray sources, which are coincident with UV sources. And there's blue in points show that such a distribution, which is they're being studied. There is another galaxy which is you see the H alpha images which highlight the H2 regions, and then optical and then UV-8 image, which is much sharper and shows mostly hot stars. And this is a galaxy image to the UV-8 image. You see this is the clarity and individual structures, individual stellar images in UV-8M. Well, this is a small part of that thing, and this is again compared with HST, and how do you coordinate between HST and then UV-80 image? This is being studied by Canadian friends. I'll skip these things in a rush, and they go to Virgo cluster of galaxies, again UV-80 and compared to CFHT. Both optical combined UV studies are being done. Well, again, this illustrates the galaxy image to UV-80 image. Galaxy is a blob, and you could see the various structures now. And let me, this is a very interesting galaxy which is being investigated by Koshi George and Annapurni and a few others, where this is a stripped material from this galaxy forms star formation. They're studying the star formation, which is in stripped part. They're now doing a set of such galaxies and very intense work, which I won't be able to cover you in detail. Now, let me to illustrate to you something which we just completed a paper on for uh, for this 5 years celebration of UVIT, and then submitted recently 2 days back for to describing our planetary nebulae studies. Planetary nebulae, you might have an idea of what it says. It's a main sequence star, like stars which are heavier than the sun, go through this evolution of becoming a red giant, which is bulges and the waves, and then again goes to the after core helium burning. It goes to the horizontal branch and then again goes to the asymptotic giant branch. There, the massive mass loss happens in the star. And the final burst, which is called superwind, itself is ejected. And the star starts with the nucleus, which is almost like a pre-white dwarf. It starts contracting and becoming hotter and hotter and provides the ionizing radiation to illuminate and interact with the material which is through is ejected earlier. And this excited material starts radiating in these various emission lines, which make this glow. And that also tells us the story about how the mass loss happened and the nuclear enriched material which came out of the outer layers of the stars. For example, S processed elements are made in these kinds of ejecta in this AGB stars. And so to study all that, we need, and luckily it provides this hot radiation glows. And sometimes it's also, as it's getting hot, it is also, there is a stellar wind. This wind interacts with this material, and then there is a shock fronts, and so to really understand. So this is shown how it goes through the main sequence in the top right. You see that normal yellow star becoming red supergiant, and then ejecting the planetary nebulae, and finally ending up as a white dwarf, that white dot. And this circular material which is around that thing is called planetary nebulae, which disperses in interstellar medium, with enriched metals from the interiors of stars. This happens between stars between slightly more massive than Sun to almost 8 or 10 solar masses. So it's many stars' life is that way. So what our interest was to study these interactions of stellar wind with ejecta and the ionization structure of it, and maybe to ultimately trying to get the various abundances and so on and so forth. But one of our examples is first one we observed is NGC 40, what is called the blue part is the X-ray in, emitting regions which are mapped by Chandra's satellite. And in our UVIT image on carbon 4 line, the same regions have been seen in an entity inside. So we could correspond these to that, and then we can build up a 10 to the 6 degree thermal gas to 10 to the 4 or 10 to the 5 degrees thermal gas. And so we can build up an ionization model and then get at the physics of that. And what came out as a great surprise was the whole nebula, which you see optically in X-ray, is contained in this small circle here. Outside of it, there is a big halo, and that is only seen in one filter, one which is we only had one filter, ultraviolet, 16 at 1680 angstroms centered filter, and in the shorter wavelength. So it was only radiate. We could see this big halo of the ring only in that part, not in the slightly longer wavelength. So for example, the left image on this shows no halo, whereas the right one does halo. And what is this nature of halo? Is a big mistake. This is a good discovery. We didn't know the existence of this before. And this turns out to be the fluorescently emitting H2 molecule, cold H2 molecule, which has been sitting there ejected. Probably when it is in the passing through the AGP phase, it's slowly expanding and dispersing away, but there is no thermal radiation, temperature, thermal activity for that to be seen in other emission lines. So it is this cold gas when they're ionizing photons, hot photons go and hit it, the H2 molecule get excited and re-radiates back as fluorescence. So that is what is giving us. So we could detect cold gas in the ultraviolet region, which is hot. This is itself a discovery in the sense we didn't know that it was existing. And this is repeated in a much dramatic scale in another object called butterfly nebula. Whereas the
Professor
optical
Rao,
nebula is, as is
Professor Rao,
shown in this newspaper
hello.
ad, newspaper item.
Prosper, can
That
you hear me?
optical image is the one on the left, yellow. And when we saw that in the UV, for UV, you see it's much bigger the UV emitting, far UV emitting gas. Not only that, there are two jets. So that goes to tells us that history of the mass loss, how the star ejected, it says this thing, and how much mass is unseen there. So there was a big missing mass problem. That is what happens when the star of 8 solar masses or something becomes finally a zero point 0.6 solar mass white dwarf. Where is the rest of the mass? So only the glowing mass is only part of a very small, only partially known. So where is the rest of the mass? So this cool gas, which is unseen so far, except for UV, was lying there. So we had to quantitatively estimate, and there is this itself is a unknown so far. We couldn't see, and we studied few more nebulae, which is a recent one. This is not uncommon. Many of these so-called bipolar nebulae seem to show this kind of halo and sometimes jets, which are marked in here, seen in selectively because of our advantage that we could image in various filters. We could actually discern these new halos, which is very exciting. And it's actually one can go back, age them depending on the expansion velocity. We can say probably when it was ejected, how the interactions are going to go. And this is very, very strange objects. Not only this went through one phase of going from a red giant to planetary nebulae stage, and instead of becoming the star becoming a complete white dwarf, it's again coming back. Okay, coming back and then doing it for a double time. There are many, many interesting things which came out of this study. And well, this is, and I don't have time to describe to you, but this is the nearest, most interesting object called Helix Nebula compared to we compare here with HST images. You see the clumps in HST are also seen in ultraviolet. And so this was our major effort, first attempt. Then what is the next? Where are we going to go from here? I'll just quickly, within 1 minute, run you through this. This is apparently using the Aditya has a UV experiment which is being done in IUCA for the solar investigations, and IIA has already proposed a spectroscopic high resolution imaging telescope. I believe I don't know the details, which is Annapurni is probably will provide. And Jayant is building all kinds of payloads with in UV and experimenting with the detectors to satellites, payloads from not only in our country, from anywhere else, international, with Chinese and so on. What I would finally like to tell you is is explored between 10,000 angstroms, 1200 angstroms longward. But there is a whole region between 900 and 12,000, which is called Lyman UV. And that is very rich in this thing, and we should try to study that, both imaging and high resolution spectroscopy, to do many interesting things. So this is a photograph of the anniversary, which was of first or second anniversary of the launch, after lunch. And I would like to end up with a small poem which was written by Sri Sri in Telugu. It reads, Nenu Saitam Vista Srishti Ashruvakkati Dharapusana. And in the English translation, probably not exactly appropriate. Maybe you can read that. And with these few words, and my thanks to many of the people who were involved in developing UVIT and ASTROSAT, and also the people who contributed some of this information for me for this talk, like Raghavendra Prasad, Sri Ram, Jayan, John Hutchings, Ashok Pati, and Firoza. So I would like to thank them and thank you to give to for you to be patient and patiently listening to my grandfather's tale. Thank you very much.
Thank you, Professor Rao, for a very interesting
Hello?
talk. Yeah, can you hear me? Yes. Hello?
Hello?
Yeah. Thank you, Professor Rao, for a very interesting talk. And we'll now open it for discussion, maybe, for one or two questions, quick questions.
Can I start, Aruna? This is Jayant here.
Yeah.
So, Kameshwar, that was a fascinating history. And I must say that I very much enjoyed our time together on in the early days of UVIT. And I do think that if we had, you mentioned about the resource problem, and if we had all of what we needed right at the beginning, I do think that we would have been. I'm sorry, you can't hear me? Can you hear me, Kameshwar? Shall I go ahead?
We can hear you.
Okay.
But it looks like he is not hearing anybody.
Yeah.
Okay. It's his headphones. No, I was just saying that that it was really an enjoyable time working in the early days of ASTROSAT. And I do think that if we hadn't been resource constrained and all, we could have gone much further. Yeah, I don't think he can hear.
Yeah, it looks like he's not hearing us.
I cannot hear.
Now he.
Now you can
No,
hear?
not in particular.
What
Hello.
about? No. Okay.
I cannot hear.
Yes, we check now. Yeah, we can't hear it.
No, I
Yes,
cannot
we can
hear.
send an email later
Oh, yeah.
or telephone him.
We can hear you, but I cannot hear you.
Take out the earphones.
Okay. How do we rejoin?
Yeah, I think, Aruna, it looks like he can't hear us.
Yeah, I'm trying to call him and tell him because, yeah.
Ask him to take out at least those earphones. Just see whether the earphones are not. Let him use the computer. But anyway, it's a very fascinating talk here. Nice picture.
Nice history.
Very quite refreshing, all those slides.
I like that picture of IIA in the early days.
Yeah,
Everyone
he's trying
laughing.
to rejoin.
Yeah.
Hello. He's trying to, Kameswara Rao is trying to rejoin. Let us just wait for 1 or 2 minutes. Let's see. Yeah.
I sit here, they won't see me properly. If I sit there, and then it's nicely seen.
Raghu, can you join?
You know, Usmania would have had such a great department if they had kept
Okay. Yes. Yeah. So Professor Rao has joined, and he is still not been able to hear. But he's telling that if you have any questions, then he will try to answer through phone. So, do you have any questions, anybody? Or can you hear Rao?
No questions, but we were all appreciating the talk.
Yeah.
Please
So,
just tell him that we
yeah.
liked his presentation and his pictures.
So much. Yes.
Okay. Okay, Professor Rao. Professor Rao. So the Jayant Murthy and Anupama, everybody says like they have enjoyed your talk and they liked the pictures that you have shown, and they have all of them. They have enjoyed your talk thoroughly. So if maybe
Yeah, thanks very much.
yeah. So okay then. Okay.
Can you read the chat? Is it possible for him to read the chat?
Yeah. Professor Rao, can you please read the chat? Are you able to read the chat? Hello? Hello? I'm not getting any answer from him on from the other side. So maybe we will close the meeting.
Yeah, sure.
Yeah, and I will send him a message.
Yeah, all right. Yeah, thank you.